So in today's lecture video, we're going to talk about unsaturated hydrocarbons. Like we already studied in the previous lecture video that hydrocarbons can be saturated as well as unsaturated. So in this class, we're going to talk about unsaturated hydrocarbons, basically alkene. So unsaturated hydrocarbon, like I already told you, we already explained in the previous lecture video, there are three types: alkene, alkyne and aromatic hydrocarbons. So alkene unsaturated hydrocarbons contain double bond, alkyne contain triple bond, right? And then the general formula for alkene is CnH2n, where N is number of carbons, right? Number of carbons. So and then we're going to talk about aromatic hydrocarbons in the next video, alkynes and aromatic hydrocarbons. So one of the example of aromatic hydrocarbon is benzene, but in today's lecture video we're going to talk about just for alkene. But before we talk about alkene, let's do a couple of example on this general formula. How would you verify whether the given molecular formula which is given belongs to the alkene or alkyne or alkene? So talk about some of the example. So if we have alkane, we know alkane is what? Saturated hydrocarbons, means all are single bonds, like carbon, single bond carbon. Alkene is unsaturated, one of the unsaturated hydrocarbon that has double bond between carbon and carbon, at least one double bond. And then we have alkyne, that means we have triple bond between carbon carbon, means three bonds between the carbon. So and then the formula that we discussed in the previous video is for alkane is CnH2n plus 2, for alkene CnH2n, for alkyne is CnH2n minus 2. So where is N is the number of carbon atom that you have for that particular compound. So let me give you one example. If I have a molecular formula as C4H10. So if this molecular formula is C4H10, so this compound belongs to which part of the hydrocarbon, whether this molecular formula compound is alkene or alkyne. So how would you determine this particular formula or compound belongs to which of the hydrocarbon? So you have to just use this formula for different hydrocarbon and you can verify easily that that compound is gonna make alkene or alkyne. So let me give you this example. So how many carbon you have in this molecular formula or this compound? 4. So put this thing in this alkene formula, C4H2 into 4 plus 2. So C4H8 plus 2, which is C4H10. You got this one. And then if I use 4 in this formula, we're gonna get C4H2 into 4, C4H8. If I put 4 in here, number of carbon 4 minus 2, C4H8 minus 2, C4H6. So out of the three given formula for alkene, alkene and alkyne, only the formula for alkene satisfy the molecular formula if I put carbon number 4, right? So that means this C4H10 is an alkane, because each and other molecular formula that we got by using a different formula for alkene and alkyne, we are getting a different molecular formula, which is not exactly the one that we were given. So this is an alkane. So let me give you one more example on this. If I have C5H10 molecular formula, this organic compound belongs to alkene, alkyne, or alkane. So let's see how many carbon you have in there. N equal to 5. For alkane, we have a formula CnH2n plus 2. So C5H2 into 5 plus 2, C5H10 plus 2, C5H12. So if it was an alkane, it should have been C5H12, not C5H10. So it's not possible. For alkene, formula is CnH2n. So C5H2 into 5, C5H10. So it looks like this molecular compound belongs to an alkene. But let's verify for alkyne too with a triple bond. Formula is CnH2n minus 2, C5H2 into 5 minus 2, C5H10 minus 2, which is C5H8, which is not exactly as the formula that is given. So by looking at the formula, we know this molecular compound is an alkene because this formula is not matching up. So if the molecular formula is given, then you can easily verify that particular compound or molecular formula belongs to which part of the hydrocarbon, whether it's alkane, alkane, or alkyne, by using the formula given. Okay. Or if I ask you, if you have 5 carbon in a molecular compound consists of 5 carbon, how many hydrogen it should have to become alkane? So if any molecular formula consists of 5 carbon, how many hydrogen it has to have so that it becomes an alkane? So that means if you have 5 carbon, how many hydrogen you need to make this molecular compound as alkane? So for alkane, what's the formula? CnH2n plus 2. If I have 5 carbon, how many hydrogen we have to have? 12. That make this hydrocarbon as alkane. If I would have 7, how many hydrogen we need to make it an alkane? 16. Right? If I have 9, we need 20. Right? So what you need to do, you have to just double the number of carbon and add 2 to it. 9 into 2, 18, add 2 to it, 20. 7 into 2, 14, add 2 to it, 16. Right? So alkane. Similarly, if I ask you, if I have 7 carbon, how many hydrogen we need to make this molecular compound as alkyne? How many hydrogen we need? So we know the formula for alkyne, 2n minus 2. So you have to double it, 14, subtract 2 from it, that means 12, C7H12. If you have 12, how many hydrogen you need to make it an alkyne? So again, double the number of carbon and subtract 2 from it. 12 into 2, 24, subtract 2, 22. Same thing apply for alkene. If I have 7 carbon, how many hydrogen we need to make this molecular formula as an alkene? So formula is CnH2n. So you have to just double it, 14. If you have 13, you need 26. If you have 11, you need 22. So all of them belongs to an alkene. You have to just double it. So make sure you practice all this thing. That will help you to determine whether the molecular formula given is an alkene, alkene, or alkyne. So now let's talk about the diagrammatic representation of the geometry of alkene. Like we already discussed for alkene, the hybridization state. Similarly for alkene, for carbon in alkene you have the same orbital, and then after hybridization this electron is moved to the top p orbital, and to make an sp2 hybridization for alkene, how many orbital you need to mix? You need one s orbital and 2 of the p orbital. But how many p orbital we have? 3. So that means out of the 3 p orbital we are just using 2 for mixing, and then the one of them is remain the way it is, which is this. So after mixing 3 orbital 1s and 2p, you're gonna get 3 hybridized orbital, right? And one of the p orbital that doesn't involve or didn't involve in the hybridization remain unhybridized, right? So that's why the hybridization of this orbital normally we call as sp2. Like I already explained, we use one s orbital and 2p orbital to make this hybridized orbital. And if you can see, the energy of this hybridized orbital is less than compared to unhybridized orbital, right? And we'll see what's the purpose of this unhybridized p orbital in making an alkene molecule. So let's take an example. You have carbon, you have 3 sp2 hybridized orbital, 1, 2, 3. You have one more carbon side by side. You have 3 hybridized orbital, 1, 2, 3. Because we need a bond, and then we have 1 electron here, 1 electron here, 1 electron here. These are these electrons, right? And then you have 1 electron here, 1 electron here, and 1 electron here, which is again these 3 electrons from different carbon, right? But what about this empty p orbital? So this empty p orbital is unhybridized and present perpendicular. This is unhybridized p orbital, right? And then we have to make a hydrogen. So this is hydrogen, this is hydrogen, bind to the sp2 hybridized orbital. This is hydrogen, and this is hydrogen, right? So now you have one carbon, one of the sp2 bind to the another sp2 hydrogen, sp2 orbital, hybridized orbital, and the other 2 hybridized orbital is bound to the 2 hydrogen for each of the carbon atom, right? So now we left with just unhybridized p orbital that doesn't have that has 1 electron in here, right? This is the electron that is in the unhybridized p orbital. So what's the purpose of this p hybridized orbital is they overlap with each other. They overlap, they just come together and then overlap, and because of this overlap you're gonna make one special bond called pi bond. Pi bond. So pi bond is normally so if I make an alkene, so C double bond C, this is hydrogen, this is hydrogen, hydrogen and hydrogen. If you can see carefully over here, this bond is formed from the sp2 hybridized orbital, sp2 hybridized orbital, sp2, sp2, and one of them is formed by sp2 hybridized orbital. And and then this bond, the second bond is a pi bond, which is made by the unhybridized p orbital. So you can see the difference. Out of the 4 bonds that carbon has, this carbon has 1, 2, 3. 3 bonds are formed from the hybridized orbital, which is sp2, and one of the bond is formed by the overlapping of unhybridized p orbital, right? So they are pi bond. So because of this, in alkene molecule, carbon has a double bond. So out of the double bond, one is sigma bond and one is pi bond. Sigma bond is formed by the overlapping of hybridized orbital, and pi bond is formed by the overlapping of unhybridized p orbital. So you have to know the difference for an alkene molecule. Okay, so I already explained about this hybridization, how the alkene normally form the double bond. And the important thing over here, sp2 hybridized alkene. So this is C double bond O, this is hydrogen, hydrogen, hydrogen. So one of them is sigma bond, another one is a pi bond, right? So this carbon is sp2 hybridized carbon, this carbon is sp2 hybridized carbon, because you have one how many sigma bond you have, and how many single bond you have? 1, 2, 1, 2 and 3. So how many orbital you need to make this 3 hybridized orbital? 3. So sp2, right? And the bond angle is 120, and this alkene molecule is planar. Planar molecule. So it's present in the plane. So make sure you know the structure of this alkene. This is a sp2 has planar molecule and the angle is 120. Whereas sp3 that we learned from the previous lecture, sp3 has tetrahedral shape and the angle will be 107.5, 109.5. So you have to know the difference between which kind of carbon you have, sp2 in alkene, sp3 in alkane, and then we're gonna see what type of hybridization you will have in alkyne, the triple bond. So now let's try to solve this problem. Identify the following compound as an alkene or alkyne. So if you can see, you have a double bond in here. So one of them is pi bond. So this can be a pi bond, right? And this is sigma bond, right? So the time you see that you have two lines, parallel lines, that means you have a double bond. So that means this is an alkene, right? Okay. So now let's try to name how to name an alkene and then compare how is different than from alkane and alkyne, that we're gonna learn about alkyne later on. So in alkane we learn about the whenever you end any name for an alkane, the ending word or ending words will be ane in alkane. Similarly, if you name any alkene, the ending word or the name of the alkene should end with ene, right? For example, take this as an example over here for alkene. How many carbon you have in there? 2 carbon. 2 carbon is what? Eth. 2 carbon is eth, and then you have a double bond, that means this is an alkene, and then if this is an alkene, your ending word will be ene, so the name will be ethene. Right, so whenever you name any alkene, make sure you write the ending word with ene. So now let's try to solve this problem, or try to name for this molecular compound. So the time I see that I have a double bond over here, I know this is an alkene molecule, and I have to use an alkene rule to write the Hayflick name for this compound. So make sure the first rule says you have to give count the longest number of carbon in the parent chain, right? That we learned in the alkene molecule how to name it. But the only difference is in alkene you have to give preference to double bond or alkene instead of substituent. So you have to give the lowest number to the alkene molecule or the carbon that contain an alkene molecule rather than to the substituent. Second, always include double bond in parent chain. You always have to include a double bond. It doesn't matter whether by including a double bond you are getting the lowest number in the parent chain or some less carbon is okay, as long as you have a double bond. But try to count the number such a way that you can include a double bond as well as you are getting the longest chain as your parent chain. But if it's not possible, then you have to still give to preference to the double bond and include the double bond. That's the only difference that you have to make sure you know this thing. So now let's try to name this molecule. Now let's start counting from 1, 2, 3, 4. I can go 5 down, I can go 5 up. So it doesn't matter whether I'm going up or down, doesn't matter. So I'm going up, so I'm going to remove this is one way of counting. Second way of counting is I can start from here 1, 2, 3, 4, 5. I could have gone 3 over here, but this is not possible because I can get more than 3. So that's why I went to the left side. So as you can see in my parent chain, I'm including a double bond in each of the parent chain, whether it's red counting on the green color marking. I'm still getting a double bond in my parent chain. So even though if I started from here 1, 2, I'm getting a substituent on the second carbon, but I'm getting a double bond on the third carbon, right? But if I use a red color marking 1, 2, I'm getting a double bond on the second carbon. So it doesn't matter whether I'm getting a substituent on the fourth, 1, 2, 3 on the fourth carbon. It doesn't matter as long as I'm getting the lowest number on the double bond. That's my priority is. So I have to start the counting from left to right, not from bottom to left, right? So now let's start counting 1, 2, 3, 4, 5. This is my parent chain. And then so you have to write the substituent on the fourth carbon, what you have, methyl group, and you have to write the location of the double bond. You have to specify where the double bond is situated in the compound. So you have to write the location of the double bond 2, and then you have to write you have 5 carbon pent, and then ene, because this is an alkene. So 4-methyl 2-pentene. You can write the same name differently. You can write the same name like 4-methyl pent 2-ene. So I just moved the 2 in between the name pent and ene, so it's also okay. So as long as you are specifying where the double bond is, it's good, right? So both the names are correct, right? Okay, so let me give you one more example on this. If I have CS3, CH2, then I have CH, not CH, I have C double bond O, CH2, 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 CH3. So this is one more organic compound that has a double bond because this is an alkene. So let's try to pick or name this organic compound. So first try to pick the longest carbon chain that also include a double bond. So can I start from here? 1, this is free and I can start 1, 2, 3, 4, 5, 6. Is it the right one? No, you cannot start counting from here because in this parent chain you are not including a double bond. So this is wrong counting. So make sure you have to include a double bond. So we have to start counting from this carbon. 1, 2. If I go up 3, 4, but I can see easily that if I go down I can get more than 5, so I'm not going up, right? So this should be our parent chain, not the one that I did with the green pen, right? Because in that one we are not including the double bond, but we have to. So this is your parent chain. Now we have to know which end you have to start counting. Either you have to start count from left to right or right to left. Now we have to see. So we have to start from right to left. Why? Because if I go from right to left, the first carbon, the lowest number carbon will get the preference, which has the double bond, right? If I would have started from left to right, 1, 2, 3, 4, then the fourth carbon will get a double bond, so which is not the lowest number. I can easily get number 1. So this is the counting that is correct. 1, 2, 3, 4, 5. Then this is our substituent, right? And then the substituent has 1, 2 carbon, which is ethyl. Right, so the naming will be 2-ethyl 1-pentene, because we have 5 carbon, that's why it's pent. En is a double bond, and where is the double bond is situated? On the first carbon. So this is the name that you can get, 2-ethyl 1-pentene. Right. Okay, so make sure so let me give you one more example on this and then we'll go forward. CH3 CH, CH3 CH, double bond CH2. So what should be the name for this molecule? So we have to give the priority to the double bond. So we have to start from here, 1, 2, 3. I can go up, I can go down, doesn't matter, both are 4. So let's pick the straight one. So the name will be 3-methyl. This is your substituent, 3-methyl 1, this is 4, 4 is butene, so 3 methyl 1 butene. Or you can write 3 methyl just butane. If you don't write 1, we are assuming that is on 1. So if you don't write anything, we always assume this is present on the first carbon. But if it's present on the some other carbon, second, third, you have to specify the location where the. So this is a solution from the problem that we just did. So you can have a look. And the name is we already talked about. So now let's talk about a cycloalkene. Like cycloalkene is also a cyclic compound, is a ring shape, but the cyclo compound has a double bond in it, right? So cycloalkene has a double bond within a ring structure. So the same rule will apply. You have to give the preference to a double bond, doesn't matter where the substituent is attached on the cycloalkene, right? So let's say for this example over here, even though the substituent is attached, which is CS3, we are not starting the counting from this carbon. Why? Because we have a double bond and we have to give the priority to the double bond, and after that we have to give the priority to the substituent. So we have to start from this carbon and then we have to start 1, 2, 3. So on this, by starting from this carbon, we are putting a double bond on carbon number 1, so we are giving the priority to it. So the name will be 3-methyl. On the third carbon you have methyl group attached, and then this is cyclopent 5 carbon, and then because this is alkene, so cyclopentene, and we are not specifying the number 1 in here, location of the double bond. Why? Because if we don't specify, we are assuming the double bond is between carbon 1 and 2, that means is on the 1, right? So let's try to name this following cycloalkene. Again, the same principle apply. You have to give the priority. You start 1, 2, 3, 4, 5, 6. I can write cyclohexene, or I can write cyclohex1ene, right? I'm just specifying the location, or I can write cyclo1hexene. So all of them are correct names, but depending on if you don't specify, that's also okay. So let's try to solve the second one. Again, you have to specify 1. You have to give the preference to a double bond 1, 2, 3, 4, 5. On the third carbon, if you can see, you have 2 different methyl group attached to the same, because carbon has 4 bonds. 1 bond is here, 1 bond is here. Now you have 2 different bonds attached to the same carbon. This is methyl, this is methyl substituent, right? So what should be the name? I can write 3, 3, because both the substituent is attached on the same carbon, so the location will be the same, 3, 3. Then you write dimethyl, because you have 2 methyl group, that's why you are writing di. And then you have to write cyclopentene. So this is the name of this compound, 3,3-dimethyl cyclopentene. So let me give you one more example on this, some extra problem. So if I have this compound, this is double bond, you have one this. So what should be the name for this compound? So again, you have to specify, you have to give the preference to the double bond 1, 2, 3, 4, 5, 6. After double bond, you have to give preference to the substituent. So that's why you are not going this way, you are going opposite way. This is wrong, right? So the naming will be 3,4 dimethyl cyclohexene, because this is a 6 carbon ring, right? Cyclo closed rings, 3,4 dimethyl cyclohexene. So this is the solution of the previous problem. So now let's try to solve some more problem on naming of alkene. So you have CH2, C double bond CH, CH double bond CH2, and then you have one more example. Yes. So how are we going to name both this compound? So you have to give the preference to the double bond. If I start from here, 1, 2, 3, 4, I'm giving the preference to the double bond on the first carbon and then the fourth carbon. If I would have started from the other side, 1, 2, 3, 4, still I'm getting the double bond on the first carbon as well as on the fourth carbon. So it doesn't matter which end you have to start counting, both will give the same priority or same location number of for both of the double bond. So now let's try and let's see if we start from left to right. If we are assuming this is the right number of counting, so I can write the name of this as 1, 3. How many carbon we have? We have 4 of them. 4 is bute, so bute. And then how many double bond we have in here? We have 1 on the first and 1 on the fourth, right? Or 1 on the third, right? So 1, 3 bute. Then you have to write di and then in. So why I'm writing di? Di means they specify that you have 2 double bond at location 1 and 3, and you have 4 carbon parent chain, and then this is alkene. So the name will be 1, 3 butadiene, or you can write 1, 3 butadiene. So diene tells you about you have 2 double bonds. So make sure you write dienes or it will be a wrong name, wrong naming of the compound. So let's try to solve the other one. So again you have to start giving the preference to a double bond. 1, 2, 3, 4, 5, 6. So in this case I'm giving the preference to the double bond, 1 on the first carbon, another one on the third carbon. If I would have started the numbering from this side, 1, 2, 3, 4, 5, 6. So still it doesn't make a difference, because still with the green pen we are getting the one of the double bond on the number 1 and the second double bond is on the third, like we had for the previous numbering system. So it doesn't matter which numbering system you're gonna use. So I'm gonna use the blue one. And then try to name this molecule. This will be 1, 3. Then you have to write cyclo, this is important, and then you have 6 carbon hexa, and then you have 2 double bond, that's why diene, right? So make sure this is important, don't forget to write di, because you have to specify you have 2 double bond at 1 and 3. So the name will be 1,3 cyclohexadiene. So now let's talk about the geometrical isomers present in alkene. So we already talked about the geometrical isomers in cycloalkane in the alkene chapter. So geometrical isomer is normally present where you don't have any free rotation across a carbon-carbon bond. So in double bond, because of this double bond, it's very hard to rotate these 2 carbon across this double bond, because if you rotate, then the pi bond is going to break. So because of this pi bond, we cannot rotate a carbon-carbon across a double bond. so they are fixed, rigid. So if you have, let's say this one, this is alkene, carbon number 1, carbon number 2, and if you have two groups attached to the carbon on the same side of the carbon double bond, then we have cis. If the two groups is attached on the opposite side or opposite plane of the carbon double bond, one is above, one is on the below of the plane, then we have trans, like the same way we have for cycloalkane. So this is cis, this is trans, and then why this is 2-butene? Because you have to number it 1, 2, 3, 4. So cis because they are on the same side, and 2-butene is because the double bond is present on the second carbon, cis 2-butene. This is trans 2-butene is still same, 1, 2, 3, 4. This is trans, they are upon the opposite side, and then 2-butene, the name is same, but the location or the spatial arrangement of the groups are different, even though they are connected with the same carbon. The connectivity is not disturbed, right? But the location of the group is different in the space. So let's try to solve some problem on this geometrical isomers of alkene. So let's try to solve the first one. So I can write CH you have C, you have H, you have Cl, you have double bond, you have C, you have H, you have Cl. So in this case if I drew the compound like this, that means both of the Cl group is on the same side of the plane of the double bond, that is, this is cis isomer. If I would have drawn opposite way, C double bond C, one of the chlorine is on the top, hydrogen on the bottom, hydrogen on the top, chlorine on the bottom. Now they are in the opposite side of the plane, so this is trans. So depending on how you normally draw, you can make cis and trans isomer from this compound across the double bond. Now let's try to solve the second one. So if you have C, you have H, you have H, double bond, you have C, you have H, you have Cl, right, on this. So this compound cannot make a cis and trans. Why? Because on the same carbon you have the same group attached. So this is the requirement for a geometrical isomer, that the same carbon doesn't have both the substituent or both the same substituent. So cis and trans is not possible for part B. And then for part C, let's try to solve this. For part C, you have carbon, double bond carbon, you have H, you have Cl, you have H, you have CS3. So now you have, for each carbon you have two separate group, and the same group is present on the same side of the plane. This is cis. If I would have drawn the same compound like over here, H on the top, Cl on the bottom, in this case CS3 on the top, H on the bottom. Now H is and H is on the opposite side of the plane, so that means this is trans isomer. So you have to remember that you cannot have the same group attached on the same carbon. If it's there, then you cannot make a cis and trans isomer. That's the only requirement that you need to know. Right, so this is the solution that we already talked about in the previous slide, and they are easily explained on this slide. Then you can have a look. Again, for part B also, the no geometrical isomer is present because one carbon contains both the identical group that we already discussed. And then for part C also, we can have cis and trans. And then what's the name of this is chloropropene. Why? Because you have to give the priority to the double bond. 1, 2, 3. 3 is prop. Ene is because you have a double bond on the first carbon, and on the first carbon you have chloro, and then this is in the cis form. both is on the same side. Right, so this is cis 1 chloropropene, this is trans because they are on the opposite side, right, of the plane. Okay, so now let's talk about a couple of the reactions that normally alkane gives. Alkenes are very chemically reactive. They normally give certain chemical reaction, and one of them is addition reaction. As the name is saying, addition means when you add across a double bond, you add something. So let's take an example. You have a carbon-carbon double bond and you have to add one molecule of any compound, A bond B, then the bond is gonna break. A will go to across one of the carbon, B will go to the second carbon, and then you will see A and B is attached to both the carbon, and then one of the bond is going to break, right? So that means whenever you have an addition reaction, you are converting an alkene to alkane, because now you have all single bonds, no double bond is present. So whenever you do an addition reaction, always remember you're converting alkene to alkane, right? Because if you don't break this double bond, each carbon will get 5 bonds, which is not possible. So you have to break one of the double bond in here, so that each carbon still have, after attaching the A and B, still have 4 bond in there. So there are couple of addition reaction that you need to study for this class. One is halogenation reaction, one is hydrogenation, and the third one is hydration reaction. And then we're gonna discuss each one of these reactions separately. Talk about halogenation reaction first. So halogenation means when you add halogens across a double bond. So this is an alkene, this is halogens, this is Br2 molecule, bromine gas. So you have bromine bond bromine. Okay, so bromine bromine. So what's gonna happen? You're gonna break this bond. One of the bromine will attach to one of the carbon containing double bond, another one attached to the second carbon that contain a double bond, and this double bond is going to disappear, one of them, and then you will get 2 bromine and 1 single bond in here, right? So this is the addition, and you are making haloalkane, means on alkane you have halogen attached. So now this is an alkane molecule with halogens attached. So let's see the one of the actual chemical reaction that is going on. You have 1 butene, 1 2 3 4, 1 butene react with Br2. The bond is going to break. One of the bromine will go to the second carbon, second bromine go to the first carbon, and the bond is going to break, or else carbon will have 5 bond, which is not possible. So you have to break a bond. So now you're making a bond, and the name will be 1,2-dibromobutane, because you have 4 carbon. This is your parent chain, right? So this is second one is hydrogenation reaction. What is hydrogenation reaction? When you add hydrogen across the double bond, means hydrogen bond hydrogen. So let's see the general reaction. You have a double bond, you have a hydrogen, you have to break the hydrogen. One of the hydrogen will go to the one of the carbon that contain a double bond, another hydrogen will go to the another carbon that contain a double bond, and the bond will, one of the bond will be broken down, and you will get a single bond between carbon and carbon. And again you are converting an alkene to an alkane, right, through addition reaction. So let's take an example. You have 2 butene, 1 2 3 4. You have 2 butene, you are adding hydrogen gas, bond is gonna break, one of the hydrogen will go to the carbon that contain a double bond, another one go to the second carbon that contain a double bond, and then you will have hydrogen attached across it. So you're converting an alkene to alkane, butane, because you are going to have a single bond in here. So you have to remember hydrogenation means hydrogen, addition of hydrogen. Halogenation means addition of halogens. And now to talk about the hydration reaction. But before we goes to the hydration reaction, we have to specify or learn about a specific rule called Markovnikov rule. This is one of the important rules that you need to know to carry out this reaction. So according to Markovnikov rule, let's take an example. You have this alkene, right? 1, 2, 3. This is propane, or 1 propane. And then if I add any hydrohalogen over here like HCl, over here, hydrochloric acid, so this is called hydrohalogenation. But forget about this thing, just remember we have HCl. So what's gonna happen? Hydrogen and chlorine gas bond is gonna, hydrogen and chlorine atom bond is gonna break. Now you have to decide, out of carbon number 1 and carbon number 2, hydrogen will go to which carbon. You have to see, hydrogen can go to this carbon or hydrogen can go to this carbon. So you have to decide. So this scientist tells, or this rule tells you that rich get richer. What does it mean? So that carbon that already contain high number of hydrogen will get the hydrogen from the hydrochloric acid, HCl. So out of the CS to first carbon and second carbon, which carbon has the highest number of hydrogen? Carbon number 1, you have 2 hydrogen in here, compared to the carbon number 2 that has only 1 hydrogen. So that means rich get richer. Hydrogen will go to that carbon of the double bond that has high number of hydrogen. So basically, so the right moment will be this one. Hydrogen is going to get to the first one, and the chlorine is gonna get to the other one, and you're going to get a product CS2. You're gonna get hydrogen over here, then CH, then you're gonna get Cl, then CS3. This is hydrogen, this is chlorine, right? So remember this thing, the rich get richer. This is one of the important rule, and then you're gonna use this rule in the next slide. Addition of simple acid. So let's try this. This rule, you have an alkene, 1, 2, 3, 1 butene. You have 4 carbon, which is 1 butene, and you have HBr, hydrobromic acid. So the bond is gonna break. The hydrogen will go to the carbon that across a double bond that has more number of hydrogen, rich get richer. So hydrogen will go to the first carbon, bromine will go to the second carbon, right? So you have 2 choices. Either you put bromine on the first, hydrogen on the second, hydrogen on the first, bromine on the second. So out of the 2 possible outcome, this outcome is the right outcome according to the Markovnikov rule. So this one is the main product that you're going to get, and the product will be 2-bromopropane, which is this 2-bromopropane. This is not the product, right? Let's take another example. You have an alkene, you have HCl, bond is going to break. Right now we don't know how many hydrogen you have across 1 and 2, so we don't have any option. You can either put hydrogen over here on the first, doesn't matter, then the chlorine will go to the opposite, or vice versa. So let's take an example over here. You have an alkene, 1, 2, 3, 4. So this is 2 butene again. you have HCl, you're gonna break the bond. So the hydrogen will go to that carbon across a double bond that has more number of hydrogen. So in this case 2 and 3 are the carbon that has the double bond, and both of them has just single hydrogen. So there is a tie. Both 2 and 3 has one hydrogen attached. So it's up to you whether hydrogen can go to the 2, then chlorine will go to the 3, or if H goes to the 3, then chlorine is going to get 2 to 2. So it doesn't matter which way, because there is a tie between 2 and 3. Nobody has higher number of hydrogen, both are equal. So it's up to you. So H is over here, Cl is over here, or it could have been like this: CH3, CH, CH, CH3, H, Cl. So both are right. Now let's talk about the next reaction called hydration. As the name is saying, hydration means addition of water. Addition of water, H2O, across a double bond. So you have a double bond, you have water, which is H2O. We usually write H and OH, which come as water. So the hydrogen will go according to the Markovnikov rule. Hydrogen will go to that carbon across a double bond that already has higher number of hydrogen, and OH will go to the other carbon of the double bond, right? And then this is going to make an alcohol. So later on, when we talk about this functional group OH, we will know that this is an alcohol. So right now, just remember, whenever you add water across a double bond, you always make an alcohol. So you have to just remember this thing in the presence of an acid. So so let's take some example. You have this compound alkene 2-butene, and you have to put water in the presence of acid H2SO4. The bond is gonna break. This hydrogen now again, carbon 2 and carbon 3 that has a double bond has equal number of hydrogen. So there is a tie. So it's up to you. You can put hydrogen to carbon number 2 or carbon number 3. It's up to you, or same as vice versa for OH, either 2 and 3. So in this particular case, they put hydrogen on the 2 and OH on the 3rd, but you could have done it opposite way. Both are right answer. So you can write, because there is a tie. This can be one of the answers. So both answers are correct. So now let's talk about propene, one of the alkene, and when we add water across it in the presence of an acid, what's going to happen? Now this is 1, 2, 3. So carbon number 1 and carbon number 2 has a double bond. Now you have to put hydrogen to which carbon, 1 or 2? So you have to put a hydrogen to carbon number 1, because that has more number of hydrogen compared to the hydrogen on carbon number 2. And according to Markovnikov rule, hydrogen will get to the carbon that has more number of hydrogen across a double bond, and then OH will go to the second carbon, and then you're gonna get this product, and again you're gonna make an alcohol. So if you know how to use a Markovnikov rule, then you can make easily all the product. So make sure you know what is Markovnikov rule is. This is very important. So now let's try to solve this reaction using Markovnikov rule. So what should be in the presence of an acid? What's going to happen? The bond is going to break. Now you have carbon number 1, 2, 3. So then so this is a double bond. So the hydrogen will go to which carbon? Carbon number 1, because it has 2 hydrogen. Whereas carbon number 2 of the double bond doesn't have any hydrogen, so the chlorine will go to the second carbon, and then you're gonna make CH3 CH, CH3, CH2, and then you're gonna make Cl over here and H over here according to the Markovnikov rule. So make sure you practice this type of problem. This is very important. So this is the solution that we already covered. How does that product is gonna form? I already covered all this thing. I already explained, but you can also read it out from here. Why we got that product, and the name of that product will be 2-chloro-2-methyl propane. Because 1, 2, 3, this is 2-chloro. On the second you have, this is your parent chain. This is also substituent, this is substituent. So 2-chloro, we have to write alphabetically. C comes first in M, so alphabetically is 2-chloro-2-methyl propane.